Hi, my name is Thomas Price, and I'm an assistant professor at North Carolina State University, where I direct the HINTS lab. Our research focuses on how to help students learn how to program. And in particular, we look at how we can use AI and data-driven technologies in order to make that learning more effective. Today, we're going to be talking about how to make learning more effective in K-12 computer science education.
K-12 computer science education continues to grow rapidly. For example, the AP/CS Principles course has doubled in size from its inception in 2016 to 2019, and now has over 100,000 students taking the test each year. Importantly, the number of women and students of color taking this course continue to grow at or above the rate of all students. Courses like these are critical for ensuring equitable access to computing education, and supporting students in these courses is particularly important. However, K-12 computer science courses face a challenge. Unlike in other subjects like math or science, where instructors usually trained for their specific subject that they're teaching, many computer science instructors don't have a professional CS background. Instead, they've taken a few weeks of professional development in order to prepare to teach the course. These teachers are doing an amazing job of supporting their students, but it can be difficult to debug challenging code issues or to scale their support to an entire classroom. This creates an opportunity for automated support. If the programming environment can help students resolve challenges and answer questions and make progress, then teachers can spend their time helping the students who need it the most. However, there are a few challenges that make it difficult to create technology that can support students in CS classrooms. The first challenge is that many of the assignments that students are working on are creative and open-ended, like making apps, games, and simulations. These can have many possible correct solutions and many ways to achieve them, and often students can customize their solutions with creative elements. Traditional modeling approaches in AI don't often work here. Expert rules can't support all solution paths like they can in another subject like algebra. Another challenge is that students in these courses often use visual and interactive programming environments like Scratch, Snap, Alice, or Processing that allow them to create these open-ended assignments. And these platforms support complex inputs like mouse and keyboard inputs, and complex outputs like moving sprites around on a screen. Traditional support tools that we have in computer science, like test cases that check whether a student's code matches the right output when given the right input, simply don't work here because the inputs and the outputs are too complex. However, computer science education also presents us an opportunity to make use of data-driven methods. Programming data is rich and complex. It's structured like natural language. For example, a set of program code in the block-based Snap language can be deconstructed into an abstract syntax tree, where each block has a relationship to each other block. Programming data is also sequential and fine-grained. For example, here we see a variety of students' attempts at solving a single programming problem. Even though all students start in the same state, they end up in a variety of different solutions and take different paths to get there. We can analyze this sequential data, or set of traces. And each of these traces consists of individual snapshots, corresponding to students' code at a given point in time. Today I'm going to talk about how we can use this rich, fine-grained, and sequential data in order to support students and instructors in K-12 classrooms. I'm going to give a couple of examples, including data-driven hints, sub-goal-based feedback, predictive models, and analytics to inform instruction. The first example I'm going to talk about is a system I developed called iSnap, which offers automated hints and other forms of feedback to students as they program to address the first problem we discussed, where students are stuck, but teachers may not be available or equipped to help them. iSnap extends the block-based environment Snap, And here we see an example of a student working in iSnap on a simple programming assignment called the guessing game, where the first part of the assignment requires them to welcome the player to the game, ask their name, and greet them by name. The student is stuck because of a simple bug, where they used the plus operator to join two strings together, when in reality they have to use the join operator. The student tries to type in welcome into the blank but can't, so they ask for help. iSnap then highlights their code with red highlights indicating blocks that don't belong in a correct solution, and yellow blocks that belong in a correct solution but may be in the wrong place. This allows the student to know to get rid of this plus operator that's incorrect, but keep the answer block, because that is part of a correct solution. The student might work for a while and try to get to the correct solution from here, but if the student is still stuck, they can ask for a next step hint. These hints suggest blocks that they can add to the solution to get closer to a correct solution. So if the student clicks on the blue outline in the say block, they'll be suggested to add a join block, which is the correct solution to this part of the problem. They can see from the color that that should be found in the Operators tab, and then they can try adding it. As soon as they do, their code immediately updates with a new set of feedback, showing that their answer block belongs in the second part of the join operator. When the student has resolved their issue, they can dismiss the hints and continue working on their own. iSnap generates its hints using an algorithm called source check, which takes as input those fine-grained, structured, and sequential programming data we were talking about earlier. In particular, it takes in a set of traces, or correct solutions, from prior students working on a given assignment, for example, from another semester. The source check algorithm also takes as input a partial student solution and a time at which a student is requesting a hint. The goal of the algorithm is to output a suggested next snapshot or edit for the student to work towards. The approach that we use is solution-based. We first identify a target solution. We survey a variety of candidate solutions and select the most appropriate for hint generation using a special distance function. We next construct a path to that solution, and then take the first step in that path as the suggested hint for the student. While this algorithm is relatively simple, resembling in some ways a nearest neighbor algorithm, it actually performs quite well. When compared to other hint generation algorithms, including deep learning-based approaches, source check performs quite well, better than almost all other algorithms on a textual Python dataset, and the best in the block-based iSnap dataset, comparing only unfavorably to human tutors and gold standard hints. Now I want to talk about how we took iSnap's data-driven hints and applied principles from learning sciences and HCI in order to make them more effective, because having a data-driven algorithm is not enough to promote learning. This is work led by my PhD student Samiha Marwan and my collaborator Joseph J. Williams at the University of Toronto. One disadvantage of automated hints is that they only show a student what to do, but not why. Students often gave us feedback that they didn't understand hints, even when those hints ended up being useful or the correct answer. To address this, we added textual explanations at the bottom of hints, explaining what they were useful for or why they were being suggested. Students with textual explanations perceived hints as more useful, more relevant to their code, and more interpretable than hints without these explanations. And when asked to explain the purpose of a hint, students were better able to articulate what it was telling them to do. This is important because our prior work suggests that students' perceptions of hints are important for how often they're used by the student. However, explanations alone did not improve students' performance or learning when accompanied by hints. Another challenge with automated hints is getting students to not only progress as a result of being given a next step, but also to learn from that to perform better in future assignments. To address this, we added a self-explanation prompt to the hints, encouraging students to think about why Snap recommended the hint or how it could be used in their own code. We found that students who were given self-explanation prompts not only performed better on the task in which they were given hints, but they also performed better in the first half of the next task when working on objectives similar to the ones where they received hints in the first task. Well, however, students who did not receive explanation prompts performed no better than a control condition without hints. This suggests that hints can not only improve immediate performance, but with the right additional prompting, they can improve some forms of learning. Another challenge with hints is that they require students to actively request them through an on-demand hint button. And this may be difficult for students who are caught up in the problem-solving process and forget to take a step back and think about what sorts of help they need. We addressed this through a proactive, data-driven hint display. With this display, we used prior students' data to recognize when students were falling behind on a problem, and we proactively offered them hints in those moments, which they could choose to click on or choose to avoid. We found that when students used this display, we saw reduced help abuse and reduced help avoidance. Students were more likely to ask for just the right amount of help. Hints aren't the only form of support that we can give students using data. I'm going to talk about other work that Samiha has done to create sub-goal-based feedback in collaboration with my colleagues Stephanie Barnes and Min Chi at NC State and Susan Fisk at Kent State University. With sub-goal feedback, students get a list of objectives in the bottom right-hand corner of their code as they work. As they progress, for example, by creating a custom block and creating a procedure for that custom block, their progress on those objectives is updated. As you see, the green progress bar has now increased. Once the student has completed the first part of the objective, creating the custom block and the parameter, their progress is estimated at 50%. When they actually use it in their code, their progress increases to 95%, and they're given positive feedback encouraging them to continue. They can then check off the objective to indicate that they're finished. We found that students who are working with this adaptive immediate feedback on their progress on sub-goals had lower idle time, better performance on future tasks, and higher intention to persist in computer science compared to students who had none of the feedback. However, these sub-goals were authored by experts. So our next question was whether we could create the same effect with automatically created sub-goals. We used an unsupervised data-driven algorithm to extract meaningful features that represented correct solution code, and we clustered them together into meaningful groups. We found that while these groups weren't perfect, they did meaningfully correspond to human sub-goals, and that with a little bit of expert insight, we could combine them together to create reasonably good sub-goals that could be automatically detected in students' code without any expert authoring effort or any fancy detection algorithms. Now we're exploring how we might be able to use additional expert judgment to refine some of those detections to make them more accurate and more useful to students. An important part of any automated feedback or support for students is the ability to accurately assess students' program code, not only when they're finished, but also as they're working. The next thing we'll talk about is work by my student Emma Wang on doing so using execution traces from program code. This was work done in collaboration with Gordon Fraser and Andreas Staubauer at the University of Passau. So far, everything we've talked about has used the structure of students' code in their traces in order to give students support, the abstract syntax tree in particular. But there's an entire another source of data that's also captured by a trace, and that is students' execution traces, the actual runtime behavior of their program as they run it. So for example, in a game of Pong, we might see a ball bouncing off of a paddle, and at every frame, we can capture properties of each of the sprites on the screen, such as their X and Y position and direction, and how these change over time. We call this an execution trace. We can use this execution trace to assess students' code from their trace data. And in fact, we've found that the execution trace is often a better indicator of student performance than their code structure. For example, we might write a rule to assess this particular behavior that says when the ball is touching the paddle, then if the paddle changes direction, the test case is successful. This is called the property-based test, and it can be difficult for novice instructors to define. So we've created an interface that allows instructors to define these property-based tests and automatically run and test students' code. We've found that property-based tests that we authored were able to incredibly accurately assess students' code with very minimal errors, achieving accuracies around 100%. However, ultimately our goal is not to manually define these tests, but rather to learn them automatically from the data. And it should be possible by extracting a series of events from students' code and doing the proper feature extraction and feeding these features into a learner, we should be able to identify automatically which types of events correspond to correct program behavior and which are indicative of broken programs, which would allow us to assess students' code in real time using only labeled data and give them feedback on when they are and aren't succeeding on the requirements of their program. Next, I'm going to talk about how these same sorts of automated assessment approaches can also be used to inform instruction. In particular, we explored how to use a deep learning model called Code2Vec in order to automatically assess students' code. Code2Vec has been very effective on software engineering tasks, and we wanted to know how effective it would be at classifying student code, in particular with much smaller data sets. So we trained Code2Vec to classify whether student code passed a rubric for assessing student code. What we found was that Code2Vec did outperform other structural baselines, like an SVM and a multi-layer perceptron, trained on simple features extracted from students' code. However, the F1 scores of around 0.69 are probably still insufficient for automated feedback. However, we went a bit further, and we asked whether or not we could learn anything from the way that Code2Vec classifies code. In particular, it uses an embedding to represent code as a set of vectors. The embedding encodes information about what makes code correct. And so we wanted to explore whether this embedding revealed patterns in student code that might be useful to instructors. We used tsni to represent the embeddings in 2 dimensions, and we clustered them. What we found was that when we took students who failed a particular rubric item, for example failing to use a parameter correctly, and we clustered their code using Code2Vec's embedding, we found that those clusters corresponded to meaningful misconceptions where students would benefit from specific targeted feedback. For example, for this rubric item, we found that one cluster corresponded to students who didn't know how to use a loop at all and simply repeated program instructions manually, in green. One orange cluster that corresponds to students who knew how to use a loop but didn't understand that they could use a variable to change the number of repetitions that the loop did. And a brown cluster that corresponded to students who actually didn't know how to use parameters correctly in their program, and instead hard-coded a constant value. Now, these 3 groups need different feedback, but they all failed the same rubric item. We found that Code2Vec effectively found clusters that other types of clustering techniques would not have uncovered that could be used for this feedback. In this talk, I've shown how rich sequential programming data can be used to provide automated support for students working in K-12 computing classrooms. Thank you so much for your attention. We really appreciate it, and we'd be happy to hear from you. With any questions, please feel free to reach out for anything regarding data-driven automated support for computer science education. And one last plug, Samiha Marwan should be graduating in the fall, so if you're interested in hiring someone who can do this work, please let her know.